And before that, I was in the ion storage group in Boulder with Dave Wineland in the early 2000s. And so I got my start as an ion trapper, and I'm still an ion trapper. And today I work mostly on hardware architecture, to believe it or not. And today I want to tell you about our third generation quantum computer, Quantinuum Helios. And this conference is really about the energetics of quantum computing and trying to minimize that. And from my perspective, the biggest thing you can do to minimize energy is to build a quantum computer in the first place, right? Because it can solve certain problems with exponentially suppressed effort. And so immediately, even if you have like a large constant in front, you're going to get an exponential suppression in the energy cost. And I hope to show some of you that today. So first, this is Helios. Oh, I even get sound. This is great. So this is a machine that it just came out in November. That's the trap. It's a centimeter on a side. It lives in a vacuum chamber. That vacuum chamber lives on an optical table, sits in a cabinet, and probably is supported by 8-ish or so racks. And thanks. And that's what it looks like. That's what it looks like. And it got its start. Helios is our third generation, and it got its starts kind of on our second generation. And this is how these chips particularly look. These ion traps, there's a picture of some ions kind of floating around in our second generation. The way these machines work is the ions are mobile, and the operating zones are fixed. And we perform operations on the ions with laser beams. The ions are trapped above the surface of this chip by controlling these patches of metal, these are gold, with voltages. And we can hold ions in a particular place by setting a certain arrangement of voltages, and if we dynamically change those voltages in time, we can move the qubits. This is the heart of what we call the quantum charged coupled device architecture. And to kind of give you, walk you through maybe a tutorial level version of how it works, and this is a tutorial on how it would work in our first generation H1 device, let's just walk through this particular example of these 3 qubits here. We have a red qubit, a yellow qubit, and a blue qubit. And we're going to execute this circuit. And over here I have a kind of a cartoon of like a small segment of a linear ion trap. And so we start with initializing the qubits, and for us that means using laser beams. Okay, so these qubits are arranged in particular trap, and the laser beams are applied with those colors. And then now we want to do a 1 qubit gate, and we're only going to do them on the red and the yellow. And you'll notice that the red and the yellow are in these 2 shaded areas here. Those are the operational zones. So we apply the laser beam, and that performs this particular Hadamard gate. And now we want to perform a gate between these first 2 qubits, but they're not in the same place. And the way ion trap gates work is they actually have to be co-located to execute a 2 qubit gate. And so what we do is we move them. So we just take this yellow one, we just dynamically change the voltages applied to those particular electrodes, and we move them over, and then we join them together in a common well, and now they're ready to be gated. And we use laser beams again to perform that particular gate. We use 2 laser beams to perform 2 qubit gates. But now we want to execute, let's say, this third operation where we're going to gate between the red and the blue. And you'll notice that, well, they're not in the same location. In fact, they're not even in the right order. And so for this operation, we actually first swap these qubits, split them, move them over, rejoin them, and now they're ready to be gated. And of course, we apply the gate with these particular laser beams. Measurement also uses laser beams. The way this works is you apply a laser beam, and the key difference between a measurement and these other operations is you now have to infer the result. And the way you do that is you collect the photons. And so you shine this laser beam on resonance with this particular atom. And if it's in the qubit state 1, it will scatter many photons, and we collect that on with a big lens and a detector. And if it's in the other state, it scatters very little photons. Very easy discrimination problem. Lots of photons means state 1. Few photons means state 0. So that's kind of like the QCCD in a nutshell. But this is how we started with H1. And this is what Helios looks like today. And so that, if you look here, oh, look at this, I can use this. Maybe. Maybe not. Well, anyway, these linear segments here are actually directly mapped to the way our first generation device actually works. The laser beams just skim across the surface there. But this particular device, this Helios device, has two extra elements in it. Number one, it has this storage ring in the upper left-hand side here. And two, it has this junction in the middle. And that allows us to do some rearrangement. So zooming in here, this is actually a picture of real ions in the trap. This particular device holds 98 qubits. On the right-hand side, is where we perform all of our quantum logic. There are 8 zones here that laser beams kind of go over, and this is where all the operations occur. We have over here on this left-hand side is kind of a high-density packed storage area where qubits are live in a ring. And then right over here in the middle, we call it the cache. And so the way this works is the ring actually spins, and particular qubits that are marked for getting in the next round get picked off in this particular junction, stored in the cache. And this happens kind of in parallel to hide the latency of that particular operation while these particular gating operations happen in the quantum logic region. After those are done, the cache slides into the quantum logic. The quantum logic kind of moves off the side of the screen to the right, just to kind of be stored while the next operations occur. And that continues until this storage ring is completely depleted. Now, here's that same picture I showed you again before. It's about 8 racks. Half of them are lasers and optics. The other half are electronics. In this particular device, we have one. It doesn't look like this. We have a prototype version of this in Broomfield, and this particular device is actually being constructed as we speak and will be deployed to Singapore later this year. So now I showed you that kind of cartoon walkthrough on how this device actually works. This next video kind of shows it in a much more marketing fashion, but with some really great music. But this is an ion. It's kind of a 2-dimensional array of ions here, or atoms, if you will. And they first start, you load the trap. So the trap is first initially unloaded, and there's a hole in the trap. And I'll show you this right next, is that neutral atoms are loaded through this hole. They're ionized with laser beams, and then the trap is loaded. This is the storage ring. You can see 2 qubits highlighted here, and they're picked off by this particular junction, moved into the operational regions where the laser beams actually exist to perform the operations. And that kind of shows you kind of at a high level how this particular device actually works. So this device was released in November, and it has a lot. Just having those basic features gives you a lot of advanced features just for the quantum computer itself. Because the qubits actually move, you immediately get all-to-all connectivity. And to kind of illustrate how that works and contrast it with fixed qubit topologies, is I have this kind of 2-dimensional array of 9 qubits here. If you only had connectivity limited to nearest neighbor and you wanted to gate between far qubits, you'd have to actually execute several swap gates in order to kind of communicate the information from one end of the computer to the other. But because we can move our qubits, we get direct all-to-all connectivity immediately. And this actually has a lot of advantages, in particular for getting high encoding rates and error correction, single-shot error correction, as well as just reducing the depth and the error in a computation at the physical level. We have very high fidelity gates. This is another mark of the quantum charge coupled device architecture. The main reason that we achieve these high fidelity gates is because we have isolated zones that only operate on 2 qubits at a time. And lastly, we do have this ability to perform mid-circuit measurement. And so again, because the qubits are isolated in single zones, when we do measure them, it doesn't contaminate the qubits nearby because the laser beam doesn't scatter into those directions. After we measure the qubit, it can be reinitialized, and that measurement result can condition future operations in the quantum computer. We've benchmarked this machine, and I'll show you some results here in the next chart or two to kind of go through some of these details. But the thing I want to highlight here, maybe this will work now. It does. Okay, the key metric I want to highlight here is this average infidelity for 2 qubit gates. So we're currently measuring a little less than 8 times 10 to the minus 4. And that's a very good error rate. I would say it's the best that anyone's ever measured in a commercial quantum computer. And this allows us to, this is the key element to be able to do, circuits that outperform classical computers. It's also the key element to do to try to build fault-tolerant quantum computers. So the way we measure this is we use a technique called randomized benchmarking. The way this works is you construct a sequence of gates that are randomly selected from the Clifford group. And then because it's a Clifford gate, you can actually calculate what the inversion gate is at the very end of the sequence. And then you pick, let's say, up to 400 random gates and then append the final gate that would bring it back to the inversion to look like the identity. And then you measure how much the population decays away from the starting state. And you can see here by just extracting the rate at which that decays, you can now get an estimate for what the gate error is. And we do this for the 2 qubit gates, we do it for the 1 qubit gates, and that's actually how we get that error budget I showed you on the previous chart. Another feature of this particular computer is that when we measure qubits, we can measure whether it's in the state 0 or the state 1, or if it's leaked outside of the qubit manifold entirely. And so also with this data, we actually show what the error is in these particular gate zones with and without the leakage population. And then the total error that I showed you before, which was 8 times 10 to the minus 4, it includes the leakage. But if you condition on not having leakage, you can actually do even better if you're willing to discard some of your data. In this device, we have 8 operating zones. And for us, the gate error is a function of which zone the 2 qubits are in, not necessarily the qubits themselves. And so across all qubit pairs, you will get this 8 times 10 to the minus 4 average 2 qubit gate infidelity. And the variance is actually quite small. You can see, let's say, on this very first index, the 0, 1, it's measuring about 6. And some of the worst ones, it's measuring, a little less than 9. And so the variance is quite small in this particular gate. In addition to doing randomized benchmarking, we do what's called cycle benchmarking. The way cycle benchmarking works is you'd also have a randomized benchmarking sequence. And every other gate, you insert a very particular gate sequence, which helps isolate very specific error channels. And so we provide this data as well. It shows you not only, it actually shows you the particular polyterms that actually contribute to the error. And in particular, you'll see that it's not homogeneous. This XX and these YY terms are actually very small. And so if you can engineer a circuit that leverages those more than others, then you would actually be less susceptible to error. So now I'm going to pivot to maybe just some applications. And this is probably the first one I want to talk about where energy actually, we make a dramatic increase in energy efficiency. The random circuit sampling is a technique that was first invented by Google to show that quantum computers were more powerful than classical computers. The way this circuit works is you have, let's see here, this kind of circuit on the right-hand side here. You prepare a set of qubits here, and you construct a random set of gates moving upward, and then you finally make some measurements over here. Because we have all-to-all connectivity, we actually can construct this random circuit to have arbitrary pairings between qubits as well. In Google's original experiment, what they did was they lived within the connectivity diagram that they had in their circuit, which was a 2D nearest neighbor connectivity. And they were able to show and prove that even with that connectivity, that it is actually very hard for a classical computer to be able to construct and sample from this probability distribution. The benefit that we have is we do have this all-to-all connectivity, and this is this graph up here kind of illustrates that the qubits in this graph can connect to any other qubit. That actually increases the complexity of this particular random circuit sampling. And the consequence is when we actually do execute this circuit, the probability distributions are actually more hard to sample from than it is in the 2D case. Now, it's true that in both of these cases, the Google case and our case, that these are not simulable. And Google was accurate when they said that it took some 7 septillion years to be able to reproduce the result. And we have very similar results. Now, because we can't actually confirm it, we can't actually classically simulate it, the way we try to infer whether we're doing this correctly or not is we do what's called mirror benchmarking. And so we construct a circuit of a certain depth, and then we do the time reversal of that circuit to try to bring it back to unity. Now, you might think that could cause coherent error cancellation, but we make sure that we take special steps to make sure that doesn't happen by putting, let's say, random Pauli gates right smack in the middle, and then engineer it such that it still comes back to unity, but then can't, dilutes any effect of coherent error cancellation. And this right here is a plot of the mirror fidelity after you run it, up to depth 26. And so the thing I want to highlight here, and this is something we're proud of, is if you actually look at the fidelities that we're coming in about 0.1, 0.05 probably here at depth 06, at depth 26. It's actually very, very high. And you'll note that to be successful, you have to measure a fidelity that's non-zero up to some confidence interval, and you can see here that the error bars on this particular point are well above 0. But it's easier to measure a fidelity non-zero when you start with a fidelity that's well above 0. And most of the other experiments are done in non-ion traps. They're measuring things around 10 to the minus 4. We're measuring about 10 to the minus 1. So we did analyze how much energy cost it would take to be able to make a classical computer, be able to sample that same probability distribution in a classical way. And what we determined is that to reproduce the Helios results, it would actually take more energy than all of the stars can emit in the entire universe. And that's this right-hand plot here. So here's the sun, at 10 to the 27 watts, and it takes about 10 to the 49 watts, and that's about what Helios has, and that's the estimate of how much power is being generated by all the stars in the universe. And the reason that is because it's very hard to simulate these machines. And so we have kind of two results kind of overlaid on this left-hand plot here. The blue curves are the experiment that we performed in H2 about a year prior. And then these other curves are the Helios data that was taken. And if you had unlimited memory, then in principle, like you live on this dashed line right here, okay? And it's about 10 to 13 watts for Helios if you have unlimited memory. But if you're memory constrained, you can do, let's say, some tensor network contraction methods that would allow you to continue to compute, but you now have to spend more cycles to overcome your memory limitation, and now these curves start going up like this. Okay, but in particular for the Helios data, if you were memory unconstrained, you would live here around 10 to the 23rd watts. But if you have memory constraints, now you start living on these curves here. This is where you kind of get that 10 to the 48 watt number that we're talking about, because there is no computer in the world that has that much memory. Okay, now random circuit sampling, it's a good benchmark, because if you can't do it, then you don't have a quantum computer that's advantaged. But it's not that useful, because really you're just sampling random circuits. But we did do some other applications, and the one that I want to tell you about first is simulating the modifications of the Fermi-Hubbard model to explore high temperature superconductivity. Now, there's a phenomena in superconductors that you can take a material that's non-superconducting and then shine a laser pulse on it, and it will turn superconducting for a few picoseconds. There are some experiments to this effect. I believe this reference here is this experiment where they actually measure this in the lab in this particular superconductor. And we wanted to see if we could try to model this on our Helios machine. And then that's exactly what we did. And so we first start with this Fermi-Hubbard model, and we prepare a low energy state. We apply a light pulse in the model. We let the system evolve using Trotter-Ice dynamics, and then we measure the pairing correlations. And what you see in the data, let's say this particular shaded area is the same model being simulated classically in the past. Now we've extended it to this larger model, which has not been simulated yet. So this previous classical simulation was 14 sites, and we're doing it on 36 sites, 6 by 6. So here is the data. So we first prepare this low energy state. We inject this light pulse, and we're going to measure pairing correlations. So the pairing correlations, what you want to look at is like alternating bright, dark, and it's just checkerboard pattern. And right here at this time equal 0.75 t is like the peak, that's the very end of the laser pulse. Right here, time 0 is where we initiate this pulse. And then the pairing correlations propagate, and they propagate to times this 1.125 over t, which is well past the end of the pulse. And so if we can kind of average over like a staggered averaging pattern here, we can plot this over here, and you'll see that as a function of time, the pairing correlations start in a low state, 0.05. They jump up to a very high state, 0.25. That's this particular plot right here. But then they actually remain high, higher than they started, for 2 time points after. And so this model does show light-induced superconductivity. And what I want to tell you is that this has not been seen before because no one's ever simulated it classically before, and we believe this is actually very hard to simulate classically. So this is an example where you do get energy advantage because you can now do something on a quantum computer that you couldn't do on a regular computer. Before we did this on H2 about a year ago, we also did a similar experiment, not looking at fermions and superconductivity, but instead looking at quantum magnetism. The basic idea here is we want to prepare a thermal state of the transverse field Ising model, evolve it in time using Trotter-Ice dynamics, and then measure the correlation function between magnetization. And we do that in 2 regimes. We do it first, we have an ability to tune what the starting state energy is. And we first do it in a regime that's classically simulable. And we use a technique called zero noise extrapolation. This is an error mitigation technique. And the way that works is, you start with some raw data here. This is actually what we measure on the quantum computer. And then we inject noise. This is the NA stands for noise amplified. And then we can then take these points and extrapolate back to the zero noise level, and we get these blue points here on this line. And this is in a regime where we're not near the phase transition boundary, and it is classically simulable using tensor network techniques. And the tensor network technique used is called matrix product states. And there, the parameter that makes it complex, classically complex, is called this bond dimension chi. And you can do a similar technique to zero noise extrapolation, but on the classical side, where you start with like low bond dimension and simulate this, and increase the bond dimension, and try to extrapolate to the infinite bond dimension. And when you do this in this area where it actually simulates, these curves actually agree. And it's kind of proof to us that maybe our techniques that we're doing are working well. Well, the next thing we do, we move off in this phase boundary area where we don't think it's classically simulable, and we apply the same techniques. And so, again, we have this noise amplified case. We have the raw data. We zero noise extrapolate, and we get these points here. But we do the same thing with the bond dimension extrapolation, and it just, it goes off the page. So at least this technique is struggling. Now, recently, Google actually did, with a lot of brute force, was able to simulate these results. And they did publish a paper on it just several months ago. And so I would say, for this particular paper at 56 qubits, it was pushing the limits of what could be simulated classically, but it took a lot of effort classically to be able to replicate this data. But the Helios machine now at 98 qubits, we believe, is extremely hard to simulate. Okay, so those are a couple applications you can do at the physical level, but where we're headed is into the fault-tolerant level. And so we're now trying to use Helios to build kind of small fault-tolerant algorithms and small fault-tolerant demonstrations. And we did the following. So just like that quantum magnet, it was a 2D transverse field Ising model. We've now constructed a 3-dimensional model and used this XY model, and we constructed some error correcting and error detecting codes. And we did the following. The first is we were able to develop these codes at distance 2 and distance 4. Distance 2 are error detecting codes, and distance 4 can be error corrected as well as error detected. When you have an error detecting code, you have a way of measuring whether an error occurred or not. And if you did find an error, you just know an error occurred, but you don't know how to fix it. And so what you do is you just discard the data and continue. And that's what we did when we simulated this XY model. And we simulated this XY model both physically and error corrected. Okay. And what I want to show you here is that the fidelity, the circuit fidelity, again, we use a mirror benchmarking technique. the circuit fidelity for this error-detected scheme was about 10 times higher than the same physical counterpart. So now we're starting to move into, let's say, logically advantaged algorithms. Similarly, in this paper, we are able to show with these distance 4 codes that we could perform repeated error correction. And we actually saw, and for these distance 4 codes, we actually saw 0 errors in about 5,000 trial runs of that repeated error correction cycle. And we can say that the QEC cycle is upper bounded by 4 times 10 to the minus 5 for logical gate errors for memory. On the error detected codes, we actually were also, for this particular experiment, we operated in a partially fault tolerant way. We executed, arbitrary angle ZZ rotations in a partially fault, in a not fault tolerant way, but everything else was fault tolerant. But we were able to kind of characterize all the errors on that universal gate set, and we were able to show that all the errors were around, 1 times 10 to the minus 4, about 10 times lower than the physical errors. So maybe I can, let's see, actually, I have a couple minutes. In a previous experiment, we were able to show that we could make magic states and inject them into the code and then use them for non-Clifford gates. And we were able to show, controlled Hadamard fault tolerantly at 2 times 10 to the minus 4. And so I'd say, we're making progress towards logical gates. But maybe to finish up, I do want to tell you this computer isn't just hardware alone. It does come with a full software stack. Everything I told you about is at this lowest level down here. But we also have Guppy, which is it's an advanced programming language that allows users to write their programs in text with arbitrary control flow. You can write if statements, else statements. You can write for loops, while loops. You can make function calls, etc. It's also a heterogeneous programming model where you can write quantum code and classical code in the same file, and the quantum code can make calls to the classical code, and then wait for the response from the classical calculation to feed back to the quantum computer to make conditional branches. Not just conditional gates, either do this gate or not do this gate, but you can go down a whole program sequence in an if block, for example, condition on that measurement, and all of that runtime actually runs in real time on this runtime software. So the whole stack management and dynamic control flow actually runs on the hardware directly, just directly as you wrote it. And that programming language in our software stack is part of our Nexus platform. And I wanted to just highlight that this Nexus platform isn't just for the single software developer, it's for the community of developers. It's there to allow, it's there not only to provide a programming language, but to provide a platform to have both Quantinuum provided libraries, but user-defined libraries injected and third-party tools. In fact, if you want to write in CUDA-Q, it can compile directly to our systems. If you want to write in Q# with Microsoft, it compiles directly to our systems. If you want to interoperate between CUDA-Q and Guppy, that's available to you as well. And if you're a third-party company who wants to write tools for our platform, we make this available to you. In fact, we encourage it as well. To help build this ecosystem, this platform Nexus is where it all lives, but we do have 2 partner programs. One is called QNet. This is a user forum where people are engaged with our hardware and writing programs and sharing experiences with each other. And QSP is our quantum startup program. This is where we want startup companies who want to use our hardware to be able to develop for our hardware, and we want to encourage that, and we will give access for good programs. To finish, I just want to highlight where we're headed. So I just highlighted Helios here, but where we are headed is we are trying to build a 1 million qubit machine in the early 2030s. We have 3 machines that are planned on a roadmap to be able to get us there. And Sola is our next product coming out next year, about twice as big as Helios. It's a 2-dimensional product, and this is kind of our scalability launching point for our particular hardware, because you can rearrange qubits much more efficiently in 2D than you can in like this storage ring and these linear traps that we had before. But after Sola is complete, we'll scale it to a larger variant in Apollo 2 years later, and then tiled chips of Apollo are going to be, or will be used to form Lumos. Maybe with that, I'll just stop and take some questions.
few questions.
Hello, Chris. Nice presentation. Could you explain a little bit the role of cryogenics in your system? Because you never mentioned that. And how is it scaling when you grow in the number of physical qubits? And also, why is there so big a discrepancy in the use of cryogenics among the trapped ion vendors? Some of them use it, others don't, for reasons you may elaborate. Is it important, and how is it scaling?
We do use cryogenics, but I do want to differentiate between like a 20 Kelvin cryogenic system versus a 10 millikelvin cryogenic system. It is 3 orders of magnitude, and it's much easier and much cheaper to run at 20 Kelvin. We just flow liquid helium at 4 Kelvin, and we let it operate at slightly above its liquid temperature. It's not required, but it's helpful, and this is why there's a discrepancy amongst ion-trap quantum computers, because you can operate an ion-trap quantum computer at room temperature. The reason we use helium is for vacuum. Okay, it's for 2 main reasons. One is for vacuum, because cold surfaces make atoms stick to them and you get better vacuum. And the second is it does reduce a particular error source called anomalous heating. This is effectively like noise sources that are on the surface of the chip itself. Now, we use flow cryostats, and we actually have a building level liquid compressor, and we recapture, in the high 90% of all of our helium so that we don't actually waste helium. And we actually, our deployed systems have their own self-contained, cryostat, and it is a pretty big energy hog. How does it scale? Well, the liquid helium will scale with the power usage, just like an HVAC will scale with the power usage. But I would say it's not the dominant source. It's probably like 20%, to be honest, of the total system cost when we scale to 1 million qubits. The largest fraction for us is going to be the laser system.
Any idea about the total power cost of the Lumos generation?
Well, I do have the number, but it.
Don't talk about it.
I'm not ready to share it yet, but it's going to be substantially less than like Frontier, for example.
I think there's time for 2 more quick questions.
So I was going to ask the number also for the power consumption. I want to maybe dive a bit in the compiler, because you said that you do that in real time, but do you have an idea of, like, does this involve using HPC, or is this something that can run on a normal computer? Will it imply an increased energy consumption if we go to higher number of qubits and things like that? What's your thoughts on this?
We have a real-time controller that's embedded with the quantum computer itself. It's a combination of FPGAs, ASICs, and regular compute. It is not an HPC. We do not see an HPC necessary for that purpose. Yeah, so the runtime is physical hardware that's running. The compiler is also not HPC. It is based in the cloud, but it's not significant. It's not an HPC, not even close. Single node probably.
Last questions.
Is it me? Okay. So you mentioned NVIDIA CUDA-Q, and all the idea of CUDA-Q is about tight coupling with the HPCs. But as far as I can see, you are stuck in loose coupling. Is there a reason for that, or is there some kind of secret tight coupling going on in the background?
With NVIDIA in particular, it is tight coupling, because NVIDIA we're using for decoding for QEC, and it's going to be embedded with the machine. And so in that particular case, it is tight coupled.
You have to send it to the cloud in the public.
No, we have GPUs resident locally with the machine, and we have a tight, fast, high network bandwidth communication between those two. But it's not an HPC center level of compute. It's like a handful of cards.
Okay, that's it. So let's thank Chris again for a very informative talk on what Quantinuum is up and up to.